In this video, we'll be talking about ground-to-ground projectiles. We have this question here. It says that we have a soccer ball that was kicked at a speed of 22 meters per second at an angle of 65 degrees to the horizontal. What I'm going to do here is I'm going to actually draw it so that way I have a better sense for what the question is asking. So I'm drawing the ground. So this is the ground here. We have a soccer ball that was kicked with a speed of 22 meters per second at an angle of 65 degrees to the horizontal. So basically what that means is we have a soccer ball that was kicked initially like this in that direction. You'll notice that as the ball was kicked like that, it takes this trajectory that goes in the air, reaches some high point, and then eventually comes back down to the ground, and it hits the ground at this point right here. Okay? According to what the question says, it tells us that the angle at which the ball was kicked, and they're referring to this angle right here, is 65 degrees. So our theta is 65 degrees to the horizontal. I'm actually going to write that right over here. All right. What are the respective horizontal and vertical components of the initial velocity of the ball? So kind of what we're seeing right now, this is our initial velocity. And the initial velocity is actually being hit at an angle. It's going diagonally, as you can tell. Now, anything that goes at an angle has both a horizontal component, which is signified with this line right here, and it also has a vertical component, signified by this line right there. All right, so here again, here's our horizontal, and here's our vertical. Anything that goes at a diagonal motion has both a horizontal motion and a vertical motion. We say it has a horizontal motion because it's going sideways, or actually it's going horizontally. You can tell that the ball is actually being thrown this way. At the same time, it's also gaining altitude. It's actually going up until it reaches a high point, then it comes back down. So as you can tell, we have both a horizontal and a vertical component that's happening at the same time. So we need to signify that, and those are what those two sides are representing. I'm going to label this side right here. I'm going to label it as V initial X. All right, and our side right there, I'm going to call it V initial Y. All right, so again, our V initial X is our initial velocity in regards to the horizontal X axis, and our V initial Y is our initial velocity in regards to the vertical axis, the Y axis. The question is actually asking for both of these. So we need to know these two sides of the triangle, these two sides of the triangle. Keep in mind that we do know that our initial velocity is 22 meters per second. And what they gave us was this part of the triangle. Okay. And we're asked to solve for the V initial X on one side of the triangle and our V initial Y on the other side of the triangle. Now, you'll notice that, again, it gave us an angle, and it gave us one of the three sides. So we can actually solve these two sides with no problem at all. All we have to do is go back to our trusty mnemonic, SOHCAHTOA. We're going to look at our trigonometry functions here. We're going to use them in order to solve for these sides here. I'm going to go ahead and solve for our V initial X first. So before I do that, let me go ahead and label my sides. This side right here, that's your adjacent side, because our adjacent side is touching the angle. This side right here is our opposite side, because it's opposite. This side right here is opposite of the angle. And this side right here, the longest side, is our hypotenuse. let me go ahead and actually, what I'm going to do is I'm actually going to blow this up so that way it's a little bit bigger. You can be able to see it a little bit better. So let me go ahead and do that right now. Okay, so this is a replica, magnified replica of the triangle that you're seeing right here. We're asked to, again, to solve for our v initial x and our v initial y. I'm going to start first by solving for our v initial x. So we're technically trying to solve for our adjacent. I'm going back to my SOHCAHTOA mnemonic, and it looks like I'm going to use my cosine because my cosine calls for a cosine theta, which is cosine theta, like that. You can also say, you can just even plug in the value right now. Cosine of 65 equals adjacent, which is, again, our second letter represents the numerator, and the third letter represents the denominator. So the equation comes out to be adjacent divided by hypotenuse. All right, so our equation is looking for the adjacent. Well, the first thing we need to do is make sure adjacent is isolated. We do need to move the hypotenuse to the other side. In order to move him to the other side, we're going to multiply both sides by the hypotenuse, so just like that. And then you'll notice that our hypotenuse cancels out, and so now our equation turns out to be adjacent equals hypotenuse, which is 22 times cosine of 65. And there we go. Let's go ahead and solve it really quick. So 22 times our cosine of 65 gives me 9.297. I'm going to say 9.30. This is our adjacent, which is also known as your v initial x. And so because this is a velocity factor, we're going to say that this is 9.30 meters per second. So that's the horizontal speed of this projectile as the projectile, which is the soccer ball, gets kicked into the air. The horizontal speed, the horizontal motion, is 9.30 meters per second. I'm going to go ahead and write that down here. All right, so we've just solved for our horizontal initial velocity. We're going to go ahead and solve for our vertical initial velocity. So right now, our next part is to solve for the opposite side of this triangle. We can actually use any one of the remaining two components of the SOHCAHTOA mnemonic. So we can't use cosine, obviously, because cosine doesn't have the opposite in it. So we can either use the sine or we can use the tangent. I'm going to go ahead and use the tangent. You can use either one. You should still end up with the same answer. I'm going to, just for this video, I'm going to actually use the tangent. So the equation turns out to be tangent of 65, tangent theta, which is our angle, equals opposite divided by adjacent. And the equation is asking for, or the question is asking for the opposite because that's our initial vertical velocity. So we're looking for our opposite. That means I'm going to have to move my adjacent to the other side. So I'm going to multiply adjacent on both sides like such. There we go. Adjacent cancels out. And now our equation is opposite equals adjacent, which is what we just solved earlier, 9.30 multiplied by the tangent of 65. And then once you have that all plugged in, you can take your calculator and solve it. So let's go ahead and solve that right now. Our answer turns out to be 19.94, which I'm going to keep that in three significant figures. So I'm going to say roughly 20.0 meters per second. And I say meters per second because the opposite side of the triangle is your vertical initial velocity in regards to the y-axis. So that's your answer for this part. All right, the next part of the question, as stated here, the next part of the question is asking how long is the football, or it's a little bit of a typo here, it's supposed to say soccer ball. How long is the soccer ball in the air? So we're actually asked to solve for the time. So how long, again, how long represents time. Okay, so we're going to go ahead and solve that right now. We're going to, first of all, before I actually start working the math out, because we're dealing with projectiles, because we're dealing with motion in 2 dimensions, it's helpful to construct a horizontal vertical chart. So I'm going to write that down right here. So horizontal on one side, vertical on the other side. Okay. Let's go ahead and label the components that we know so far. So based on what we know, we'll start with our horizontal components. We do know our initial horizontal velocity, also known as v initial x. And our v initial x is 9.30 meters per second. That's all we know so far. We don't know anything about the distance or the time. However, I'm going to write them right here. I'm going to start with the time first. We're trying to solve for that actually. Keep in mind that the time exists on both factors, both the x and the y components. Let's go ahead and turn our attention to the vertical components. One of the obvious ones that we know so far is what we just solved earlier, a v initial y. Your v initial y is 20.0 meters per second. We also know that our gravity is also taken into account. That is negative 9.80 meters per second. Now I do want to bring your attention to this side of the drawing in particular. One of the concepts you have to know in regards to projectile motion is that whatever components, whatever initial velocities you find, if it's the overall initial velocity or our initial vertical or our initial horizontal, whatever those values might be, and as well as the angle itself, 65 degrees, whatever the angle they give you, whatever values you find on the initial side, that also applies to the final side as well. In other words, what I'm trying to say is that triangle that we have here is the exact same triangle that happens there. So I'm going to go ahead and draw that right now so you can kind of see it in a more clearer sense. So our final velocity is 22 meters per second. This right here, this side, this is actually your velocity final y. That value is the same value as what we found here for our v initial y, which is 20 meters per second, but we're actually going to label it as negative 20 meters per second. So again, v final with regards to the y, the vertical axis, is negative 20.0 meters per second. And the reason why it's negative is because the projectile is now descending downwards. So we signify that as a negative. So again, whatever values we find here is the exact same thing here. And because our v initial y is positive 20 meters per second on the initial side, our final velocity y is negative 20 meters per second. Now our v initial x, keep in mind, if you've seen my previous video on projectiles from the ground, keep in mind that the horizontal velocity remains consistent all the way throughout the entire trajectory. So that means, because we found our initial horizontal velocity to be 9.30 meters per second, that's the exact amount of speed that we get at the final velocity with regards to the x-axis. So the final velocity x is also 9.30 meters per second. And I'm going to keep this number positive because the projectile is still moving towards the right. It's still moving towards the positive x-axis. Okay, so our v final x is positive 9.30 meters per second. So why am I telling you all this? Well, because we can actually add more stuff to our vertical component here on our chart. We can now add a final vertical velocity, which we just looked at and what we just solved earlier. In this case, it's actually negative 20.0 meters per second. These are one of the more. This is one of the crucial components we would need in order to solve for our time. And because we know both our initial vertical velocity y and our final vertical velocity y, because we know both of those and we also know gravity, we can actually use this equation here. Acceleration equals change in velocity over change in time. Keep in mind that the acceleration, again, is just gravity, so I'm just going to change the a to a g. And remember that all these values here have to be in regards to the y-axis because we're looking at the vertical components only. So we're looking at velocity or change in velocity y over change in time. Okay, now you'll notice that the change in velocity can actually be broken down into smaller components. So you'll notice that can actually expand, this right here, can actually expand to velocity final y subtracted by velocity initial y, both of which we actually do have in our data sets right here and there. I'm going to go ahead and carry down the rest of the equation. So now our equation looks like this, and now we can go ahead and begin our math. Now you'll notice that our unknown is it's in the denominator. We need to make sure that it's in the numerator in order for us to solve it. So the first thing, because t is being divided by our change in velocity, opposite of division is multiplication, I'm going to go ahead and multiply t on both sides. That cancels out. Now our equation is times multiplied by gravity equals v final y subtracted by v initial y. Our time is now in the numerator, but it's not by himself. We have to move the g to the other side. So what I'm going to do next is I'm going to divide g on both sides. Our new equation is written as times equals velocity final y subtracted by velocity initial y divided by g. And once you're at this point, you're ready to solve. So I'm going to go ahead and plug in our values. So I'm just going to scroll back up to our horizontal vertical chart. So our final velocity y is negative 20 meters per second. Our initial vertical velocity is positive 20 meters per second, but because there's a minus there, we also have to account for that too. So even though the initial velocity is positive 20 meters per second, the minus does force it back to a negative. So it's actually negative 20 meters per second minus positive 20 meters per second, which ends up to be negative, divided by negative 9.8 meters per second squared. So those are your values. Let's go ahead and I'm going to go ahead and solve this in parts. So negative 20 minus 20, that's actually negative 40. And I'm just going to carry down the 9.8, negative 9.8. You'll notice that the negatives will actually cancel out, and so I'm going to do 40 divided by 9.8. And we get as our answer 4.08163.265. So our time is going to be 4.08 seconds. And that's how long the projectile was in the air. All right, we're going to go ahead and move on to the third part of our question here. The third part of the question is, what is the speed of the ball at the highest point? So we're basically looking at how fast the ball is moving at this point right here. This is mainly a concept question. It's not necessarily solved mathematically. It's mainly a concept question. What you need to know here is that at the highest point, the projectile has ceased for that specific moment in time, that instantaneous time. It has ceased to move vertically. It's only moving horizontally at that point. It's only moving like this at the highest point. Which means the vertical velocity at the apex, you can say Vy at the apex, or you can say at the highest point, is equal to 0 meters per second. However, although it's not moving vertically, it is still moving horizontally. Remember how I said that the horizontal velocity remains consistent all the way throughout? Even at the highest point, it also remains to be the same amount. Because the projectile is moving consistently at a horizontal velocity of 12 meters per second, and at the highest point it's only moving horizontally, not vertically, then the overall speed at the highest point is literally just the horizontal velocity. So at the highest point, we can say that the speed is 9.30 meters per second. And why do we know that again? Because at the highest point, it's only moving horizontally, and the horizontal speed is always constant throughout the entire trajectory. Okay, the next part of the question is asking how far does the ball travel horizontally before it hits the ground? And so in our question, the key words to look for is how far, that's distance, and horizontal. So we're looking at horizontal distance, also known as our d sub x. Okay, so basically, if you look at the diagram, the ball started here. It went through the air, and it ended right here. And so our question is asking, how far did that go? So we're looking at the distance from that point to this point, also known as our d sub x. Another name that they would say would be, what's the range? How far did that ball go? So what we're going to do is we're going to solve for that. Note that our dx is a horizontal component. We're going to actually write that here, d sub x. And when we don't know, we just solved our time in the previous question, so our time was 4.08 seconds, if you recall. Okay. Notice that because we know our v initial x and we know our time, we can solve for our dx by using this equation. Velocity equals distance over time. Keep in mind, because we are looking for d sub x is a horizontal component, which means we're only constrained to using only the horizontal data as given to us in the table. So we're going to look at v as vx, and we're going to look at d as dx. We need to solve for dx, which means we have to isolate it. It's not by itself. You'll notice that time is right below it, so we're going to have to move time on the other side. And to do that, I'm going to have to multiply time on both sides. That cancels out, and so our new equation is d sub x equals times multiplied by velocity x. And this is the equation that we will be using to solve for our range, our d sub x. All right, so we're going to go ahead and plug in our values. So d sub x is time, which is 4.08 seconds, and our v sub x is 9.30 meters per second. All right, since we know our values, we're going to go ahead and solve it right now. So we'll just take our calculator out and multiply that. So 4.08 times 9.30 turns out to be 37.944. So I'm going to just say 37.9 meters. And meters is the unit for distance. So this is how far the soccer ball has traveled when it was kicked through the air. So our final answer for our d sub x is 37.9 meters.